The earth beneath our feet holds secrets written across billions of years. Stories carved into stone and whispered through mountains. Tonight, we'll drift gently through these ancient truths, exploring how geology reveals not just our planet's past, but hints at its distant future. Welcome to Get Sleepy Science. I'm so glad you found your way here tonight. Wherever you are right now, perhaps feeling the weight of your body against the bed, or hearing the gentle sounds of evening settling around you, allow yourself to sink into this shared moment of stillness. We'll explore 100 remarkable truths about Earth's geology. From the slow dance of continents across deep time, to the patient work of water-shaping stone, to the hidden chemistry beneath volcanoes, preparing their next quiet breath. A gentle like and subscribe helps other sleepless souls discover this peaceful space too. It only takes a moment, but it means the world to us. One quiet tap, one sleepy soul at a time. For now, just let your shoulders soften. Let your breathing fall into its own rhythm. Imagine yourself drifting through deep time, where millions of years pass like gentle waves, where mountains rise and fade like slow breaths. Close your eyes and take a deep breath. You're floating in the deep ocean, where pressure and stillness create miraculous life, moving without boundaries, without destination, only the gentle sway of water currents. Let go of all limits. Let your mind drift through the quiet depths. The Earth is approximately 4.54 billion years old. Scientists determined this age through radiometric dating of the oldest rocks and meteorites, measuring the decay of radioactive elements like uranium into lead. The oldest minerals ever discovered are tiny zircon crystals from Western Australia, dated to 4.4 billion years old. These microscopic time capsules formed when Earth's first crust was beginning to solidify from a molten surface. Recent research from MIT in 2024 has identified rocks in Greenland's Isua supercrustal belt that are 3.7 billion years old and still preserve magnetic signatures from Earth's ancient magnetic field. This personal reflection follows. Imagine holding a stone that witnessed the birth of oceans, the first rains, the emergence of life itself. Every rock carries memory across timescales our minds struggle to comprehend. Plate tectonics shapes our world through the slow movement of massive crustal plates. Earth's outer shell is broken into approximately 15 major plates and dozens of smaller ones, each drifting at speeds of a few centimeters per year, roughly the same rate your fingernails grow. This movement is driven by convection currents in the hot, flowing mantle beneath. Where plates collide, mountains rise. Where they pull apart, new ocean floor is born. Where they grind past each other, earthquakes occur. Recent geodynamic modeling published in 2024 by Duarte and colleagues suggests that the Gibraltar Arc may evolve into a new subduction zone that will eventually enter the Atlantic Ocean, forming an Atlantic equivalent to the Pacific's Ring of Fire. The continents never rest, always wandering, always reshaping the face of our world in their patient, geological time. The supercontinent cycle describes how continents periodically gather together and then disperse over approximately 500 million years. The most recent supercontinent, Pangaea, assembled around 310 million years ago during the late Carboniferous period. All the continents we know today were pressed together into one vast landmass surrounded by a single enormous ocean called Panthalassa. Pangaea began breaking apart around 180 million years ago, during the early Jurassic period. We are currently about halfway through the dispersed phase of the current cycle. Scientists predict the next supercontinent will form in approximately 200 to 250 million years. Various models suggest different configurations: Pangaea Proxima, Novopangaea, Amasia, or Orica, depending on which ocean basins close first. The continents never stop their dance, gathering and scattering like slow breath across deep time. Volcanic eruptions can temporarily cool the planet despite releasing carbon dioxide. When large eruptions reach the stratosphere, they inject sulfur dioxide gas high into the atmosphere. This gas converts to tiny sulfuric acid droplets that form a reflective layer, bouncing sunlight back into space. The 1991 eruption of Mount Pinatubo in the Philippines cooled global temperatures by roughly half a degree Celsius, about 1 degree Fahrenheit, for a year or two. Ash and sulfur particles in the stratosphere created a reflective layer, gently dimming sunlight before gradually settling back to Earth. The 1815 eruption of Mount Tambora in Indonesia created the famous year without a summer in 1816, causing crop failures and famine across Europe and North America. However, NASA research confirms that all volcanic carbon dioxide emissions combined represent less than 1% of current human emissions. Recent studies from 2024 also reveal that climate change itself may increase volcanic activity as melting glaciers reduce pressure on magma chambers beneath, particularly in Iceland, Chile, and Antarctica. The Earth's magnetic field protects us from solar radiation and has existed for billions of years. New evidence published by MIT geologists in April 2024 pushes back the age of this field even further. Rocks from Greenland's Isua supercrustal belt, approximately 3.7 billion years old, preserve magnetic signatures indicating a field strength of at least 15 microtesla, similar to today's field. This finding extends our knowledge of Earth's magnetic field by potentially 200 million years beyond previous estimates. The field is generated by the movement of molten iron in Earth's outer core, creating a protective bubble around our planet called the magnetosphere. Without it, solar wind would strip away our atmosphere, making Earth more like Mars. The magnetic poles wander over time and occasionally flip completely, though the last reversal occurred 780,000 years ago. Earthquakes occur when stress builds up along fault lines until rocks suddenly break and slip. Most earthquakes happen at plate boundaries, where tectonic forces create constant pressure. Recent discoveries from 2025 gently remind us that earthquakes can happen even in regions once thought stable. Ancient faults, buried for millions of years, can slowly strengthen in darkness, and when conditions change, they may quietly awaken. Even the ground we consider solid holds memory of ancient stresses. The 2024 Calama earthquake in Chile surprised scientists by occurring at unusual depths and breaking past expected thermal limits. The energy released during earthquakes generates intense heat. Laboratory experiments from MIT in September 2025 show that friction during an earthquake can melt rock instantly, reaching temperatures of thousands of degrees in milliseconds. The ocean floor is the youngest part of Earth's surface, constantly being created and destroyed. At mid-ocean ridges, magma rises from the mantle and solidifies, forming new oceanic crust. This process, called seafloor spreading, pushes older crust away from the ridge at rates of a few centimeters per year. Eventually, this old, cold, dense oceanic crust reaches subduction zones where it sinks back into the mantle. The oldest oceanic crust currently found is only about 200 million years old, located in the western Pacific. In contrast, continental crust can be billions of years old because it's too light and buoyant to subduct. The ocean floor is effectively recycled every few hundred million years, making it Earth's most dynamic and youngest geological feature, constantly renewed like skin growing over an ancient body. Diamonds form deep within Earth's mantle under extreme pressure and temperature, then are brought to the surface by volcanic eruptions. Most diamonds crystallized between 1 and 3 billion years ago at depths of 90 to 120 miles beneath the surface. South African diamonds analyzed in September 2025 revealed nickel-rich metallic inclusions, providing the first direct evidence of chemical reactions occurring deep in Earth's mantle. These tiny inclusions show how oxidized melts interact with the lower mantle, offering a window into processes happening far beyond our reach. Diamonds act as time capsules, preserving samples of deep Earth chemistry. The journey to the surface occurs during rare, explosive volcanic eruptions, called kimberlite eruptions, which travel at speeds exceeding 400 miles per hour, fast enough to carry diamonds upward before they can transform back into graphite. Fossils provide windows into ancient life and environments. They form when organisms are buried rapidly, usually in sediment, and minerals gradually replace organic material. The oldest fossils confirmed are stromatolites, layered structures created by ancient microbes, dating back 3.5 billion years. Recent discoveries from the University of Tokyo in 2024 found living microbes in mineral-filled veins within 2 billion-year-old rock, suggesting life can persist in extreme environments far longer than previously thought. The fossil record reveals mass extinction events where most life disappeared, often linked to volcanic activity or asteroid impacts. 5 major mass extinctions have occurred. The most recent 66 million years ago when an asteroid impact helped end the age of dinosaurs. Fossils remind us that the life we see today is just one chapter in a much longer story of biological transformation. Glaciers carve landscapes through the slow grinding of ice against rock. During ice ages, massive ice sheets covered much of North America and Europe, sculpting valleys, creating lakes, and depositing vast quantities of sediment. Recent analysis from NASA in 2024 used satellite measurements to track glacial retreat worldwide, revealing that glaciers are losing mass at unprecedented rates. In November 2025, scientists discovered that around 9,000 years ago, East Antarctica experienced dramatic melting when warm, deep ocean water surged beneath floating ice shelves, causing them to collapse. This scientific imagination suggests glaciers are Earth's patient sculptors, working on timescales of thousands of years, yet retreating at visible speeds in our lifetime. The landscapes we call permanent, the valleys, the lakes, the rolling hills, are actually temporary features carved during Earth's cold phases, destined to change again. Sedimentary rocks form in layers, with older layers typically at the bottom and younger layers on top. This principle, called superposition, allows geologists to read Earth's history like pages in a book. Each layer records environmental conditions when it formed. Sandstone suggests ancient beaches or deserts. Limestone indicates warm, shallow seas. Shale forms from mud in quiet waters. Geologists examining rock formations can identify ancient shorelines, river systems, and climate patterns from millions of years ago. Recent research from August 2025 overturned conventional geology by demonstrating that meandering rivers existed long before plants colonized land. Stanford researchers found evidence that rivers formed complex, sinuous patterns over 2 billion years ago, suggesting that carbon-rich floodplains shaped climate for billions of years. Sedimentary layers are Earth's memory, preserving evidence of vanished worlds beneath our feet. Minerals are the building blocks of rocks, each with specific chemical compositions and crystal structures. Over 5,000 mineral species have been identified, though only a few dozen make up most of Earth's crust. Quartz, feldspar, mica, calcite, and amphiboly are among the most common. Research published in 2025 revealed that critical minerals like lithium, cobalt, and germanium, essential for modern technology and defense, are already being mined across America, but most are currently wasted as mine tailings. Scientists have begun working to extract these valuable elements from mining waste. Some minerals form only under specific conditions, acting as indicators of past environments. Garnet suggests high pressure. Halite indicates evaporating seas, and ice itself is technically a mineral. Minerals are Earth's alphabet, combining in countless ways to write the story of our planet's chemistry and history. Erosion gradually wears down even the mightiest mountains. Water, wind, ice, and chemical weathering work constantly to break rock into smaller pieces and transport them away. Rivers carry approximately 20 billion tons of sediment to the oceans each year. This is erosion in action. Mountains dissolving grain by grain, traveling through rivers, ultimately settling on distant seafloors where they may, millions of years later, become new rock. Chemical weathering occurs when rainwater, slightly acidic from dissolved carbon dioxide, slowly dissolves rock minerals. Physical weathering happens when water freezes in cracks, expanding and splitting rock apart. Plants contribute by growing roots into crevices, gradually prying rocks apart. Mountain ranges like the Himalayas or the Rockies appear permanent to human eyes, but over millions of years, they will be ground down to gentle hills. Research from 2025 suggests that if plate tectonics eventually stops in about 1.45 billion years, erosion will continue, eventually flattening Earth's mountains to rolling plateaus. Earth's mantle makes up about 84% of the planet's volume. It's not liquid magma, as sometimes imagined, but solid rock that flows very slowly over millions of years, like an extremely viscous fluid. Heat from radioactive decay and residual heat from Earth's formation drives convection currents in the mantle. Hot material rises slowly toward the surface, cools, and then sinks again. These currents power plate tectonics, pulling old oceanic crust into subduction zones and pushing continents across the surface. During the Mesozoic era, between 250 and 120 million years ago, ancient seafloor sank deep into Earth at what's now the East Pacific Rise, and those slabs are still detectable deep in the mantle today. The mantle is Earth's slow-motion engine, operating on timescales of tens of millions of years. Limestone forms primarily from the shells and skeletons of marine organisms. Over millions of years, countless tiny sea creatures die, and their calcium carbonate shells accumulate on the ocean floor. Compression transforms this biological debris into solid rock. The white cliffs of Dover, the pyramids of Egypt, and countless building stones worldwide are limestone. Some limestone began as coral reefs in ancient tropical seas. Others accumulated in deeper waters from microscopic plankton shells. When limestone is buried deeper and exposed to heat and pressure, it transforms into marble. Limestone landscapes develop characteristic features like caves, sinkholes, and underground rivers as slightly acidic groundwater slowly dissolves the rock. Looking at limestone, we're seeing the preserved bodies of billions of ancient organisms. Their lives transformed into stone that lasts millions of years longer than the creatures themselves did. Continental crust differs fundamentally from oceanic crust in composition, thickness, and age. Continental crust averages about 20 to 45 miles thick and is composed mainly of lighter rocks rich in silica and aluminum. It's less dense than oceanic crust, which is why continents stand higher and don't subduct. Oceanic crust is only about 4 to 7 miles thick, made of denser basalt rich in iron and magnesium. The oldest continental rocks are nearly 4 billion years old, while the oldest ocean floor is merely 200 million years old. This difference exists because oceanic crust is constantly recycled through subduction, while continental crust is too buoyant to sink. Continents are Earth's permanent features in a sense, fragments that have survived multiple cycles of supercontinent assembly and breakup, growing slowly over billions of years. Geothermal energy comes from Earth's internal heat, accumulated over billions of years from radioactive decay and residual heat from the planet's formation. Temperature increases with depth at an average rate of about 15 to 30 degrees Celsius per kilometer. In volcanic regions, hot rocks lie closer to the surface, making geothermal energy more accessible. Iceland derives much of its electricity and heating from geothermal sources, tapping into heat from the mid-Atlantic ridge. Geothermal power plants drill into hot rock formations, inject water, and use the resulting steam to generate electricity. This is essentially fossil heat, energy that has been stored in Earth's interior since the planet formed. Unlike solar or wind energy that depends on current conditions, geothermal represents the slow cooling of our planet itself, a resource that will remain available for millions of years. Igneous rocks form from cooling magma or lava, and their texture reveals where they solidified. Granite forms deep underground where magma cools slowly, allowing large crystals to grow. Basalt forms from lava that erupts at the surface and cools quickly, creating fine-grained rock. The Sierra Nevada mountain range in California is largely granite that solidified from massive underground magma chambers. The Hawaiian Islands are built entirely from basaltic lava flows. Pumice forms when lava full of gas bubbles cools so quickly that the bubbles are trapped. creating rock so light it floats on water. Obsidian forms when lava cools almost instantly, creating natural glass. Each igneous rock tells a story of molten material finding its way from Earth's interior toward the surface, cooling at different rates and depths, preserving information about volcanic processes and Earth's internal heat. Metamorphic rocks form when existing rocks are transformed by heat, pressure, or chemical processes without melting completely. Limestone becomes marble. Shale transforms into slate, and with more intense conditions, slate becomes schist or gneiss. The Alps, Himalayas, and Appalachian Mountains expose extensive metamorphic rocks that formed deep underground during mountain building events. During continent collisions, rocks can be buried 30 or more miles deep where temperatures exceed 400 degrees Celsius and pressure is immense. Under these conditions, minerals recrystallize, creating new textures and sometimes entirely new mineral assemblages. Some metamorphic rocks contain minerals like garnet or kyanite that only form under specific pressure-temperature conditions, allowing geologists to calculate exactly how deep the rocks were buried. These rocks preserve evidence of ancient mountain-building events, continents colliding, and the intense forces that shape Earth's crust. The rock cycle describes how rocks transform from one type to another over millions of years. Igneous rocks form from cooling magma. Then erosion breaks them down into sediments that become sedimentary rocks through burial and compression. Deeper burial and heat transform sedimentary rocks into metamorphic rocks. Eventually, temperatures may become high enough to melt rocks completely, creating magma that can solidify into new igneous rocks. This cycle operates continuously but slowly. A piece of granite might weather into sand grains, wash into the ocean, become compressed into sandstone, get buried during mountain building, and transform into quartzite. Eventually get subducted, melt, rise as magma, and solidify as granite again. The entire cycle might take hundreds of millions of years. No rock is permanent. All are temporary forms in an endless transformation. Matter constantly rearranging itself through geological time. Earthquakes generate remarkable heat along fault lines. Laboratory studies from MIT in 2025 show that friction during rock movement creates temperatures intense enough to melt minerals in moments. This helps explain the smooth, glassy surfaces found along some ancient faults. The energy stored in stressed rocks is suddenly released when the rock breaks and slips. The 1906 San Francisco earthquake released energy equivalent to detonating several atomic bombs. Yet most of that energy went into heat rather than seismic waves. The heat is often intense enough to alter minerals along the fault surface, creating smooth surfaces that can make future earthquakes more likely once stress builds up again. Human footprints at White Sands National Park in New Mexico tell a remarkable story. First dated to between 23 and 21,000 years ago, they sparked scientific debate. In 2024, researchers confirmed these ancient ages using multiple dating methods including terrestrial pollen, revealing that people walked these shores during the last glacial maximum, earlier than many once believed possible. The footprints were created when the area was a shallow lake shore. Seed layers embedded in the sediment provided material for radiocarbon dating, and researchers also dated terrestrial pollen to avoid potential errors from old carbon in aquatic plants. The footprints show adults and children walking, sometimes running, leaving behind traces of daily life from over 20,000 years ago. These tracks remind us that geology preserves not just Earth's physical history, but also records of human presence across deep time. Groundwater exists in aquifers, underground layers of permeable rock or sediment that hold water. About 30% of Earth's freshwater exists underground, far more than in all rivers and lakes combined. Some aquifers are shallow, fed by recent rainfall that percolates down through soil. Others are deep and contain water that infiltrated thousands or even millions of years ago. The Ogallala Aquifer beneath the Great Plains of North America holds water from the last ice age. Recent research from the University of Utah in 2025 studied reed-covered mounds marking locations where ancient groundwater emerges at the surface. When aquifers are depleted faster than they naturally recharge, land can sink in a process called subsidence. In some regions, groundwater depletion has caused measurable land subsidence of several meters, affecting infrastructure and increasing flood risk. The Great Salt Lake's chemistry and water balance remained stable for thousands of years until human settlement. According to research published in August 2025, scientists found that just 2 major human decisions fundamentally rewired the lake's ecological system forever. These decisions involved diverting inflowing rivers for agriculture and urban development. The lake has been shrinking dramatically in recent decades, concentrating salts and exposing toxic dust on the dry lake bed. This represents a broader pattern where human activities can destabilize geological and hydrological systems that persisted naturally for millennia. The study demonstrates how quickly human actions can overwhelm natural processes that maintained equilibrium across vast timescales. Lakes like this are sensitive indicators of environmental change, responding to both natural climate variations and human interventions. What took nature thousands of years to balance can be disrupted in mere decades. Scientists discovered 6-million-year-old ice in Antarctica in November 2025, offering the oldest direct record of Earth's ancient atmosphere and climate ever recovered. This finding represents a major scientific breakthrough, revealing a dramatic cooling trend and promising new insights into how greenhouse gases changed over millions of years. Ancient ice contains tiny air bubbles that preserved samples of the atmosphere from when the ice formed. By analyzing these bubbles, scientists can measure past concentrations of carbon dioxide, methane, and other gases, as well as temperature proxies from water isotopes. Previous ice cores reached back about 800,000 years. This new discovery extends the atmospheric record nearly 8 times further. It's like finding a time capsule containing actual samples of ancient air, allowing us to understand climate change across millions of years and better predict future trends. Let's pause here and notice your body. As you breathe out slowly, appreciate each tiny cell inside. Trillions of organisms working in silence, heart beating, lungs breathing, brain thinking, all without your command. Notice the gentle sensations on your skin, in your muscles, along your spine. You are a complete ecosystem, diverse, self-balancing. Now we continue. Earth's core is as hot as the surface of the sun. The inner core, a solid ball of iron and nickel about 1,500 miles across, reaches temperatures near 5,400 degrees Celsius. The outer core is liquid iron and nickel, and its movement generates Earth's magnetic field through a process called the geodynamo. Despite the intense heat, the inner core remains solid due to immense pressure, about 3.6 million times atmospheric pressure at sea level. Recent seismic studies suggest the inner core may rotate slightly faster than the rest of the planet. This personal impression follows, deep beneath our feet. Conditions exist that would instantly vaporize any material we tried to send there. Yet, this infernal heat is what keeps our planet geologically alive and protects us with its magnetic field. Submarine canyons are dramatic features carved into continental margins worldwide. These deep incisions rival the Grand Canyon in scale, yet they lie hidden beneath the ocean. In Antarctica, submarine canyons are widespread features driving sediment transport and affecting ocean circulation patterns. They form through multiple processes, including underwater landslides called turbidity currents, which are dense mixtures of sediment and water that flow down slopes like underwater avalanches. These currents can travel at speeds exceeding 50 miles per hour and carry enormous quantities of sediment from shallow continental shelves to the deep ocean floor. Some submarine canyons form where rivers once flowed during periods when sea level was lower. They remain as active conduits, channeling sediment from land to the deep sea, creating unique habitats for marine life along their walls. Tektites are natural glass objects formed when asteroids or comets impact Earth. The impact melts surface rock and hurls it high into the atmosphere. This molten material cools rapidly as it falls back to Earth, creating glassy objects with distinctive shapes, often teardrops, spheres, or dumbbells. They are found scattered across several regions worldwide, called strewn fields, each associated with a specific impact event. Some tektites formed from impacts millions of years ago, yet they're found hundreds or even thousands of miles from their source craters. Their chemical composition differs from volcanic glass and matches surface rocks at the impact site. Finding a tektite is like holding a piece of Earth's crust that was briefly launched into space during a catastrophic event, then returned to the surface as natural glass. Mars once had active plate tectonics, similar to Earth. According to recent geological evidence, an asteroid struck Mars 11 million years ago and sent pieces hurtling through space. One chunk eventually crashed into Earth and was recovered as a meteorite. This Martian meteorite, catalogued as Northwest Africa 16254, is a gabbroic shergotite weighing 406 grams. Analysis revealed its crystallization age and chemical composition, providing clues about Mars's early geological activity. Most planetary scientists believe Mars's tectonic activity ceased billions of years ago as the planet cooled and its interior solidified. Without plate tectonics to recycle crust and regulate atmospheric carbon dioxide, Mars lost its thick atmosphere and became the cold, dry world we see today. Earth remains geologically active, maintaining conditions favorable for life. Geologists discovered evidence for preservation of Hadean rocks, dating back to 4.16 billion years old. Within more recent geological formations, the Hadean Aeon represents Earth's earliest chapter, from the planet's formation 4.54 billion years ago to about 4 billion years ago. This period saw the formation of Earth's first crust after the magma ocean cooled. Finding Hadean rocks is exceptionally rare because most have been destroyed by subsequent geological activity or buried beyond reach. These ancient rocks provide clues about early Earth conditions, including when the first oceans formed and how quickly the planet cooled from its initial molten state. They represent some of Earth's oldest memory. Fragments that survived everything the planet has experienced over more than 4 billion years. Salt deposits on land reveal locations of ancient seas. Many inland regions, now far from any ocean, contain thick layers of rock salt, gypsum, and other evaporate minerals. These formed when shallow seas evaporated under hot, dry conditions, concentrating dissolved salts until they precipitated as minerals. The Bonneville Salt Flats in Utah are remnants of ancient Lake Bonneville, which covered much of the region during the last ice age. Germany's salt mines exploit deposits from an ancient sea that covered northern Europe over 200 million years ago. These salt layers can be thousands of feet thick, representing millions of years of evaporation and deposition. Salt is surprisingly mobile over geological time. Under pressure, it flows slowly, forming underground domes and pillars that can trap oil and gas. Banded iron formations are distinctive rocks composed of alternating layers of iron-rich and silica-rich minerals, often appearing as red and gray stripes. These rocks formed primarily between 3.8 and 1.8 billion years ago, during a unique period in Earth's history. They record the gradual oxygenation of Earth's oceans and atmosphere. Initially, Earth's atmosphere contained virtually no oxygen. When photosynthetic bacteria evolved and began producing oxygen, the gas reacted with dissolved iron in the oceans, causing iron oxide to precipitate and settle on the seafloor. These deposits contain most of the world's iron ore, the foundation of modern civilization's steel production. Looking at banded iron formations, we're seeing a frozen record of life fundamentally changing Earth's chemistry. Rust from an ancient revolution that made our modern world possible. In 2024, an unusual earthquake occurred deep beneath Calama, Chile, deeper than most, breaking past the depths where rocks normally become too warm to fracture suddenly. It offered scientists a gentle reminder that Earth still holds surprises, even in places we thought we understood. Deep earthquakes, those occurring below 300 kilometers, are unusual because high temperatures at such depths normally make rocks too plastic to fracture suddenly. Most deep earthquakes occur along subducting slabs where cooler material extends into the hot mantle. The Calama event triggered intense aftershock sequences and challenged existing models of deep earthquake mechanisms. Scientists now use seismic data to better understand stress conditions deep in Earth's interior. These events remind us that despite centuries of study, Earth still surprises us, revealing processes and phenomena we didn't know were possible, hidden in depths we cannot directly observe. Earth is slowly peeling its continents from below, fueling ocean volcanoes, according to research published in November 2025. Researchers discovered that continents don't just split at the surface during rifting, they also peel from below like layers of an onion. Computer simulations reveal that slow mantle waves strip continental roots and push material deep into the oceanic mantle, where it contributes to volcanic activity. This process helps explain the chemical signatures found in some oceanic volcanic rocks, which contain continental-derived material despite being thousands of miles from any continent. The mantle is not simply passive material beneath rigid plates, but actively participates in reshaping Earth's surface. Continents and oceans exchange material in ways that blur the traditional boundaries we imagine between them. Yellowstone sits atop one of Earth's largest volcanic systems, a supervolcano that has erupted 3 times in the past 2.1 million years. The most recent eruption occurred about 640,000 years ago, creating the enormous caldera, a collapsed volcanic crater that defines much of Yellowstone's landscape today. Heat from the magma chamber below powers the park's famous geysers, hot springs, and fumaroles. While Yellowstone could erupt again, scientists see no signs of an imminent eruption. Modern monitoring networks would detect magma movement years in advance. Visitors often inadvertently add debris and garbage to hot springs and geysers, which can alter their delicate chemistry and plumbing systems. The supervolcano beneath Yellowstone is a reminder that Earth remains volcanically active, though operating on timescales far longer than human lifetimes. Mountain ranges mark places where continents collided, or where oceanic crust subducted beneath continental margins. The Himalayas formed when the Indian subcontinent crashed into Asia about 50 million years ago. They continue rising today at nearly half an inch per year as the collision continues. The Andes formed along South America's western coast, where oceanic crust subducts beneath the continent, creating volcanic activity and crustal thickening. The Appalachians formed over 300 million years ago from a collision between ancestral North America, Africa, and Europe. Then were pulled apart when Pangaea broke up. These ancient mountains have been worn down by erosion, but still stand as evidence of ancient tectonic forces. Mountains are Earth's wrinkles, pushed up by immense horizontal forces as continents shuffle and collide across the globe. Permafrost contains frozen soil, rock, and organic matter that has remained below freezing for at least 2 consecutive years. It covers about 15% of the northern hemisphere's land surface, extending hundreds of feet deep in some locations. Arctic permafrost contains massive quantities of frozen organic carbon from ancient plants and animals. As Earth's climate warms, permafrost thaws, allowing microbes to decompose previously frozen organic matter, releasing carbon dioxide and methane, both greenhouse gases. This creates a feedback loop where warming causes more permafrost to thaw, releasing more greenhouse gases, causing more warming. Scientists are closely monitoring permafrost regions because their thawing represents one of Earth's major climate tipping points. Permafrost is frozen time, and when it melts, that time resumes, releasing consequences stored for thousands of years. Earth's atmosphere evolved dramatically over geological time, transformed by life and volcanic activity. The earliest atmosphere, shortly after Earth's formation, likely consisted of hydrogen and helium, but these light gases escaped to space. Volcanic outgassing then created a secondary atmosphere rich in water vapor, carbon dioxide, nitrogen, and small amounts of methane and ammonia, but virtually no oxygen. The transformation began about 2.4 billion years ago when photosynthetic bacteria produced oxygen as waste. Initially, this oxygen reacted with dissolved iron in the oceans, creating banded iron formations, Eventually, oxygen accumulated in the atmosphere, allowing complex life to evolve. Current atmospheric composition: 78% nitrogen, 21% oxygen, is maintained by the ongoing activity of photosynthetic organisms. Without life, Earth's atmosphere would be very different, likely dominated by carbon dioxide like Venus. Coral reefs are built by colonies of tiny animals called coral polyps, which secrete calcium carbonate skeletons. Over thousands of years, these skeletons accumulate, creating massive limestone structures. Ancient coral reefs are preserved in the geological record, sometimes found in places now far from tropical waters. These fossil reefs tell us about past ocean conditions, sea levels, and climates. The Great Barrier Reef began forming about 20,000 years ago when sea levels rose after the last ice age. However, modern reefs face threats from warming oceans. Ocean acidification caused by absorbed atmospheric carbon dioxide and pollution. When seawater becomes more acidic, it becomes harder for corals to build their calcium carbonate skeletons. Coral reefs are living geology, actively building limestone structures that will persist long after the organisms themselves are gone. Rivers have carved some of Earth's most dramatic landscapes. The Grand Canyon, excavated by the Colorado River over approximately 5 to 6 million years, reveals nearly 2 billion years of Earth's history in its layered walls. Recent research from Stanford in August 2025 revealed that meandering rivers existed over 2 billion years ago, long before plants colonized land, overturning previous textbook geology that assumed rivers needed plants to develop sinuous patterns. Rivers are powerful erosive forces, carrying sediment from mountains to seas, gradually lowering continents through erosion. They respond to climate changes, tectonic uplift, and sea level fluctuations. A river's work occurs grain by grain, day by day, but over millions of years, they can carve canyons miles deep and reshape entire landscapes. If you're still awake, still listening to Earth's secrets, that means curiosity hasn't fully rested yet. And that's okay. Take a gentle breath. Feel the weight of your body on the bed, grounded like ancient stone. We're wandering through nature's quiet wisdom together. And we'll keep going, slowly. Uranium dating allows scientists to determine the age of rocks with remarkable precision. Uranium naturally decays into lead at a known, constant rate over millions of years. By measuring the ratio of uranium to lead isotopes in minerals like zircon, scientists can calculate how long ago the mineral formed. Zircons are particularly useful because they incorporate uranium when they crystallize but exclude lead, making them ideal radioactive clocks. The oldest zircon crystals, from Western Australia, date to 4.4 billion years ago, shortly after Earth's formation. Uranium dating also helped establish the age of the solar system by dating meteorites. This technique revolutionized geology, providing absolute ages rather than just relative sequences, allowing us to construct an accurate timeline of Earth's history. Soils take thousands of years to form from weathered rock and organic matter. A few inches of topsoil might represent hundreds or thousands of years of rock weathering, plant growth, decomposition, and biological activity. Soil contains minerals from weathered rock, organic matter from decayed plants and animals, water, air, and countless microorganisms. Different parent rocks create different soil types. Granite weathers into sandy soils, while basalt creates clay-rich soils. Climate affects soil formation. Wet tropical regions develop deep soils quickly, while cold or dry climates slow the process. Modern agricultural practices can erode soil much faster than it forms. Some regions have lost most of their topsoil to erosion, a loss that would take thousands of years to naturally replace. Soil is a thin, precious interface between geology and biology. Deserts cover about 1/3 of Earth's land surface and exist for several geological reasons. Some deserts form in rain shadows where mountain ranges block moisture. Others develop in subtropical regions where atmospheric circulation causes air to descend and dry out. Polar deserts like Antarctica are technically deserts because they receive minimal precipitation, even though they're covered in ice. Research published in November 2025 revealed the potential of desert ecosystems in fighting climate change. Biological soil crusts in deserts, communities of bacteria, algae, and lichens sequester carbon and stabilize soil. Deserts are not lifeless. They're ecosystems adapted to extreme aridity. Over geological time, regions currently lush can become deserts, and deserts can become fertile as continents drift and climate patterns shift. Earth's early continents were born not from plate tectonics as traditionally thought, but from different processes, suggests new research from Hong Kong University geologists in 2025. They propose that before modern-style plate tectonics began, continental crust formed through a different mechanism involving vertical movements in a hotter, more active mantle. This challenges our understanding of how Earth transitioned from a hot, uniform surface to a planet with distinct continents and ocean basins. The first continents were likely small and unstable, gradually growing and stabilizing over hundreds of millions of years. These primitive continents may have formed and been recycled multiple times before permanent continental crust established itself. Understanding early continental formation helps explain how Earth became suitable for life. Coal formed from ancient forests that grew in vast swamps. During the Carboniferous period, about 300 to 360 million years ago, enormous forests covered much of Earth's land masses. When plants died, they fell into oxygen-poor swamp water, slowing decomposition. Over millions of years, accumulated plant material was buried and compressed, transforming into peat, then lignite, then bituminous coal, and finally anthracite, each stage removing more water and concentrating more carbon. Coal seams often contain fossils of ancient plants, preserving details of leaves, bark, and seeds. Burning coal today releases carbon that was removed from the atmosphere hundreds of millions of years ago. The energy in coal is ancient sunlight, captured by photosynthesis and stored in plant tissues, then compressed by Earth's patience across deep time. Sinkholes form when underground rock, usually limestone, dissolves and creates cavities. Eventually, the overlying material collapses into these voids, creating sudden depressions at the surface. They can appear slowly or catastrophically. In Florida, where thick limestone layers lie beneath sandy soil, sinkholes are common. Groundwater that's naturally slightly acidic slowly dissolves limestone over thousands of years, creating vast cave systems. When the roof of a cave becomes too thin to support the weight above, it collapses. Recent research identified a new category called sinkites, which reveal inverted subsurface structures and may affect carbon storage strategies. Sinkholes remind us that the seemingly solid ground beneath us is actually being continuously modified by invisible chemical processes happening in darkness below. Petrified wood forms when fallen trees are rapidly buried by sediment, cutting off oxygen. Groundwater rich in dissolved minerals seeps through the buried wood. Over thousands or millions of years, minerals gradually replace the organic material, preserving the wood's structure in stone. The result is wood that looks like wood, but consists entirely of minerals like quartz or calcite. Petrified forests exist in several locations worldwide. Most famously, Petrified Forest National Park in Arizona, where trees up to 200 million years old have been preserved. Individual cells, bark textures, and even tree rings remain visible in stone. Petrified wood is a perfect example of Earth's ability to preserve the past, transforming organic life into mineral permanence. Sea level has fluctuated dramatically throughout Earth's history, controlled by ice volume and ocean temperature. During ice ages, water becomes locked in massive ice sheets, lowering sea level by hundreds of feet and exposing continental shelves. When ice melts, sea level rises. About 20,000 years ago, during the last glacial maximum, sea level was roughly 400 feet lower than today. The English Channel was dry land, and people could walk from Asia to North America via the Bering Land Bridge. A team led by Rutgers researchers found in 2025 that modern sea level rise is happening faster than at any time in the past 4,000 years. Coastlines are temporary features, constantly advancing and retreating as ice ages come and go. Impact craters record Earth's bombardment by asteroids and comets. Most craters have been erased by erosion and plate tectonics, but nearly 200 confirmed impact structures remain. Meteor crater in Arizona formed about 50,000 years ago, when an iron meteorite roughly 150 feet across struck the surface. A 2025 study found that this impact triggered volcanic activity at the same time through interconnected geological processes. The Chicxulub crater in Mexico, buried beneath younger sediments, formed 66 million years ago from the impact that contributed to the dinosaurs' extinction. Impacts have shaped Earth's biological history by causing mass extinctions and creating ecological opportunities for survivors. They're a reminder that Earth exists in a cosmic shooting gallery. Jade has been prized by humans for thousands of years. But geologically, it's interesting because it only forms under specific conditions. Jade actually refers to two different minerals, jadeite and nephrite, which have similar appearances but different compositions and origins. Jadeite forms in subduction zones under high pressure and relatively low temperature, where oceanic crust descends into the mantle. Its presence indicates ancient plate boundaries. Nephrite forms where magma intrudes into magnesium-rich rocks. Ancient civilizations from China to Mesoamerica valued jade so highly that trade routes developed specifically to transport it. From a geological perspective, jade's rarity and the specific conditions required for its formation make it a useful indicator mineral for understanding past tectonic processes. Let each breath guide you to realize time is yours, a separate stream that only you are living, while the vast earth continues to shift, change, grow. This second you're breathing, listening, is unique. Cherish the present moment, knowing that right now, your time is unique in the universe. And we continue drifting. Stalactites and stalagmites form slowly in limestone caves as mineral-rich water drips from cave ceilings. Each drop leaves behind a tiny amount of calcium carbonate. Over thousands of years, these deposits accumulate into formations. Stalactites hanging from the ceiling, stalagmites rising from the floor. Some caves contain formations millions of years old. The rate of growth depends on water chemistry and drip rate, typically just a fraction of an inch per century. Some stalactites and stalagmites eventually meet, forming columns. These formations are Earth's patient sculptors, building stone structures one drop at a time, creating underground cathedrals decorated with mineral artworks that took millennia to form. Obsidian is volcanic glass that forms when lava cools so rapidly that crystals have no time to grow. Ancient peoples prized obsidian for making extremely sharp cutting tools and weapons, sharper than modern surgical steel. Different obsidian sources have unique chemical signatures, allowing archaeologists to trace ancient trade networks by analyzing artifacts. Some obsidian flows are thousands of years old and still have glassy, reflective surfaces. The lack of crystal structure makes obsidian especially brittle and easy to flake into precise shapes. Native Americans traveled hundreds of miles to obtain good obsidian. This scientific imagination suggests obsidian is frozen time, lava that cooled too quickly to organize itself, preserving volcanic violence in smooth, glassy silence. The moon affects more than ocean tides. Its gravitational pull also creates earth tides, slight bulges in solid rock that move across the planet as Earth rotates beneath the moon. These solid earth tides can raise and lower the ground by several inches, though the movement is too gradual for humans to perceive. Research suggests that earth tides can trigger earthquakes and volcanic eruptions by slightly changing stress conditions in Earth's crust. Some volcanic systems show increased activity during specific lunar phases, though the mechanism remains debated. The Moon and Earth remain gravitationally locked in an ancient dance, each continuously reshaping the other through invisible forces. Crystal Cave in Mexico contains some of the largest natural crystals ever discovered. Giant selenite crystals up to 36 feet long and weighing 55 tons. These grew over 500,000 years in a cave filled with mineral-rich water heated by magma below. The cave remained flooded at a perfect temperature for crystal growth. When mining operations pumped out the water in 2000, the spectacular crystals were revealed. The cave is extremely hot and humid, making exploration difficult. These giant crystals demonstrate the extraordinary results of geological patience. 500,000 years of perfect conditions creating mineral giants that dwarf humans. They're Earth's largest crystals, monuments to the power of gradual processes. Continental drift was once considered ridiculous. When Alfred Wegener proposed in 1912 that continents moved, most scientists rejected the idea. He observed that continents fit together like puzzle pieces, with matching rock types and fossils on opposite sides of oceans. But without a mechanism to explain how continents could plow through ocean floor, his idea was dismissed. only in the 1960s, when seafloor spreading was discovered and plate tectonics theory developed. Did scientists accept continental drift? This personal reflection follows. Sometimes the truth seems impossible until suddenly all evidence aligns. Continents do move, have moved, and will continue moving, reshaping Earth's surface across millions of years. Amber preserves ancient life with extraordinary detail. Tree resin, which is sticky and has antimicrobial properties, can trap insects, spiders, small lizards, feathers, and plant material. As the resin hardens over millions of years, it becomes amber, perfectly preserving whatever was trapped inside. Scientists have found ants, bees, spiders, scorpions, lizards, frogs, bird feathers, and even dinosaur feathers in amber. The oldest known amber dates to about 320 million years ago. DNA sometimes survives in amber inclusions, though not intact enough to recreate extinct species as in fictional scenarios. Amber is a golden time capsule, preserving moments of ancient life with stunning clarity. Hurricanes and extreme weather leave geological evidence. Storm deposits, layers of sand and shells washed inland by storm surges, can be identified in sediment cores from coastal regions. Scientists use these deposits to reconstruct hurricane activity over thousands of years, revealing patterns longer than written records. Recent research in 2025 emphasized that first floor elevation is a key factor in flood risk from hurricanes. FEMA and other agencies use elevation data to assess risk and set insurance rates. Geological evidence shows that powerful hurricanes have struck the Gulf Coast and Atlantic seaboard repeatedly throughout history, long before human settlement. Climate and weather leave signatures in rock and sediment. Hot springs occur where groundwater is heated by geothermal energy and rises to the surface. Iceland, Yellowstone, and New Zealand are famous for their hot springs. The water often contains dissolved minerals that precipitate as colorful deposits around the springs. Some hot spring water has been underground for thousands of years, slowly circulating through deep rock formations. Thermophilic bacteria that thrive in near-boiling water create colorful mats around hot springs. These microorganisms are among Earth's oldest life forms, suggesting life might have originated near hot springs or hydrothermal vents. Hot springs are windows into Earth's internal heat, places where the planet's warmth rises to meet the surface world. Glacial erratics are boulders transported far from their source by glacial ice and deposited when the ice melted. These rocks often differ dramatically from local bedrock, providing evidence of past ice sheets. In North America, many erratics were carried hundreds of miles from Canadian shield rocks and deposited across the northern United States. Some erratics weigh thousands of tons. Native American and early European settlers found these enormous boulders sitting inexplicably in fields and forests, not knowing they'd been delivered by ice. Erratics are frozen time travelers, rocks that journeyed hundreds of miles inside moving glaciers, then remained when the ice disappeared. Researchers used zircons and artificial intelligence to reconstruct Earth's ancient crust in 2025, revealing possible tectonic processes from billions of years ago. Zircons survive extreme conditions, preserving chemical information about the rocks they formed in. machine learning analyzed thousands of zircon compositions to identify patterns indicating ancient tectonic environments. This research suggests plate tectonics may have operated differently in Earth's early history when the mantle was hotter. Understanding ancient tectonics helps explain how continents formed and how Earth developed into a habitable planet. Zircons are Earth's most durable historians, tiny crystals that outlast the rocks around them, carrying information across billions of years. Evidence suggests early plate tectonics began over 3 billion years ago. Layers of rock at South Africa's Barberton Greenstone Belt contain scars from ancient landslides, possibly triggered by earthquakes, which may have resulted from colliding crustal plates. This 2024 finding supports the contested idea that global plate tectonics dates back over 2.8 billion years, though some geologists remain skeptical. If confirmed, it means plate tectonics has shaped Earth for most of its history. Modern plate tectonics may differ from ancient versions because Earth's interior was hotter and the crust thinner. Regardless, Earth has been geologically dynamic for most of its existence, constantly recycling and reshaping its surface. Quicksand is misunderstood. It's not a bottomless pit, but saturated sand that can't support weight. When sand becomes supersaturated with water, friction between grains decreases and the mixture behaves like a liquid. Someone who steps in will sink, but only until they reach equilibrium, usually chest deep for an adult. The danger comes from struggling, which can cause deeper sinking. The best escape method is to lean back, spread your weight, and slowly work your legs free. True quicksand is fairly rare and requires specific conditions: fine sand, upward water flow, and proper saturation. It's a temporary geological state, a moment when solid ground becomes liquid. Earth's tectonic and plate boundary evolution over the past 1.8 billion years has been reconstructed by researchers in 2024. They created a full plate model spanning 3 supercontinents: Nuna, Rodinia, and Pangaea. The reconstruction reveals that Earth experienced dynamic geological activity between 1.8 and 0.8 billion years ago, contrary to the concept of a boring billion. This period saw continuous supercontinent assembly and breakup, accretion events, and significant plate movements. Understanding this deep time plate motion helps scientists study long-term Earth system evolution, including climate change, ocean chemistry, and mineral deposit formation. Earth has never been geologically boring, always moving, always changing. Petroleum and natural gas form from ancient marine organisms. When plankton and algae died millions of years ago, they sank to oxygen-poor seafloors where they didn't fully decompose. Buried under sediment, heat and pressure gradually transformed this organic material into hydrocarbons. Oil typically forms at depths where temperatures reach 90 to 160 degrees Celsius. Deeper and hotter conditions create natural gas instead. These fossil fuels accumulate in porous rocks capped by impermeable layers. We're burning solar energy captured by photosynthesis millions of years ago, releasing carbon that was removed from the ancient atmosphere. This carbon is now returning to our atmosphere faster than natural processes can reabsorb it. Caves form primarily through dissolution of limestone by slightly acidic groundwater. Rainwater absorbs carbon dioxide from soil, becoming weak carbonic acid. This acid slowly dissolves limestone along cracks and bedding planes, creating passages that gradually enlarge over thousands of years. Some caves are vast systems with multiple levels, underground rivers, and chambers large enough to hold cathedrals. Mammoth Cave in Kentucky extends over 400 miles, the longest known cave system. Caves are still forming and changing today, though slowly. They're windows into Earth's hidden infrastructure, spaces carved by water's patient chemistry, creating darkness that existed before humans discovered it. Geodes are hollow rocks with crystal-lined interiors. They form when mineral-rich water fills a cavity, often a bubble in volcanic rock or a dissolved fossil. Minerals precipitate from the water, slowly building inward from the walls. The result is a plain rock exterior concealing a crystalline interior. Amethyst geodes can be several feet across with stunning purple crystals inside. Finding and opening a geode reveals a hidden treasure created by Earth's chemistry over thousands of years. They're mineral surprise packages, evidence that Earth creates beauty hidden from view. Crystalline secrets waiting in darkness until someone cracks them open to light. Artificial structures must withstand geological forces. Buildings, bridges, and towers are designed to flex and sway during earthquakes and wind, or they'll collapse. Research from 2025 examined how towering structures, whether buildings, geological formations, trees, or even cacti, must bend with forces or topple. This principle applies across scales. Skyscrapers have flexible foundations and frames. Geological formations like hoodoos and balanced rocks demonstrate natural engineering, surviving because their shapes and composition allow them to withstand wind and seismic forces. Earth teaches engineering lessons through geology. Structures that couldn't withstand forces have already fallen, leaving only those shaped by successful designs. Forests play crucial geological roles beyond biology. Tree roots stabilize soil, preventing erosion. Fallen trees in streams create pools and modify water flow. Research from 2025 warns that forests are falling dangerously behind in the race against climate change, unable to sequester carbon quickly enough. When forests are removed, erosion accelerates dramatically. Ancient forests created coal deposits. Modern forests affect regional climate and rainfall. Without forests, landscapes erode faster. Rivers carry more sediment, and floods become more severe. Forests are geological agents, modifying landscapes and climate, acting as intermediaries between rock weathering and soil formation, between atmosphere and Earth. Curiosity rover discovered tiny, perfectly round features on Mars while exploring Gale Crater. Scientists examined these unusual spherical formations using the rover's instruments in July 2025. They're investigating whether these spherules formed from volcanic activity, impact processes, or water-related chemical precipitation. Similar spherical features on Earth form through various mechanisms including concretions, accretionary lapilli from volcanic eruptions, or impact-related melting. Mars's geological processes differ from Earth's due to its thinner atmosphere, lack of plate tectonics, and different water history. Every Martian rock tells a story of a planet that evolved differently. taking an alternate path from Earth. Ancient riverbeds discovered in 2025 extend over 15,000 kilometers beneath Earth's surface, revealed through advanced seismic imaging. These aren't actual rivers, but channels in the mantle where material once flowed differently. Possibly ancient subduction pathways or mantle plumes that are now frozen in place. Seismic waves travel at different speeds through these features, revealing their structure. This discovery helps geologists understand mantle convection and how material circulates deep within Earth. The mantle has its own geography, its own ancient pathways, carved not by water, but by the slow movement of hot rock across hundreds of millions of years. Climate change affects geological systems in unexpected ways. Melting glaciers can trigger more volcanic eruptions by reducing pressure on magma chambers. Research in 2025 found that in Iceland, volcanic eruption rates were 30 to 50 times higher, following major deglaciation. Extreme precipitation can infiltrate deep underground and react with magma systems to trigger eruptions. 716 volcanoes worldwide. 58% of active above-ground volcanoes will be affected by more extreme precipitation as temperatures rise. Climate and geology are deeply interconnected systems. Changes to one create cascading effects in the other, sometimes in ways that accelerate change further. Earth's geological history is recorded in ice cores, ocean sediments, tree rings, and rock layers. Scientists from NASA's Jet Propulsion Laboratory use multiple proxies to reconstruct past climates. Ice cores contain atmospheric samples trapped in air bubbles. Ocean sediments preserve shells of microscopic organisms whose chemistry reflects past ocean temperatures. Tree rings record rainfall and temperature. Rocks record everything from ancient magnetic field orientation to past atmospheric oxygen levels. Each archive has strengths and limitations. By combining multiple sources, scientists create detailed climate reconstructions spanning millions of years. Earth maintains its own records, writing its history in multiple formats. Minerals show Earth's chemical evolution over billions of years. The earliest minerals formed in a simple chemical environment. As Earth cooled, more minerals appeared. When photosynthesis began producing oxygen, a vast array of oxygen-bearing minerals formed. Today, Earth has over 5,000 mineral species, many of which couldn't have existed on early Earth. Some minerals form only through biological activity or in its aftermath. This means Earth's mineralogy has evolved alongside life. Mars has fewer mineral species because it lacks plate tectonics and life-driven chemical diversity. Earth's minerals tell a story of increasing chemical complexity, driven by geological and biological processes. Continental shelves are submerged extensions of continents, sloping gently from shorelines to ocean depths. During ice ages, when sea level dropped, these shelves were exposed as dry land. Many now underwater areas were inhabited by humans and animals during the last glacial maximum 20,000 years ago. Fishermen occasionally dredge up fossilized teeth from mammoths and other extinct land animals from continental shelves, evidence of vanished landscapes. Continental shelves are biologically productive regions where nutrients and sunlight support abundant life. They're also economically important for fishing, oil and gas extraction, and offshore wind energy. Shelves are drowned continents, temporarily submerged. Weathering transforms rock from hard, resistant material into soil and dissolved minerals. Physical weathering breaks rock into smaller pieces through frost wedging, thermal expansion, and salt crystal growth. Chemical weathering alters mineral composition through reactions with water, oxygen, and acids. Together, these processes create soil and release nutrients for plants. Different minerals weather at different rates. Quartz is highly resistant, while feldspar breaks down readily. The products of weathering eventually reach the ocean where they may form new rocks. Weathering is Earth's patient dismantler, taking apart even the hardest rocks grain by grain, molecule by molecule. You might be feeling tired now. That's perfectly fine. Breathe slowly, feel the cycles. Tectonic plates move, continents drift. Rock becomes sediment. Sediment becomes stone. All are circles, cycles, endless movements. Like your breath, inhale, exhale, inhale, exhale. A small cycle within the vast earth. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like continents silently shifting, unhurried, unresisting, simply existing. We're almost there now. Ooh. Granite is Earth's continental foundation, light, resistant, ancient. Most granite is over 100 million years old. It forms when magma cools slowly deep underground, creating large crystals of quartz, feldspar, and mica. The Sierra Nevada mountains are granite. Mount Rushmore is granite. Kitchen countertops are granite. This stone has witnessed eons, crystallized from molten depths, patient as time itself. Nothing reshapes landscapes more patiently than water. Soft drops carve canyons, gentle waves smooth cliffs, rivers move mountains grain by grain, ice forms in cracks, expands quietly, splits stone. Water dissolves minerals slowly, carries them away through invisible chemistry. The soft overcomes the hard, not through force, but through endless, gentle persistence. Mountains rise and mountains fall, following rhythms spanning hundreds of millions of years. The Appalachians, once as tall as today's Himalayas, now wear rounded shoulders softened by time. Height is temporary. The persistent work of water, wind, and ice eventually returns all peaks to plains. Patience outlasts stone. Dust from the Sahara crosses the Atlantic Ocean, fertilizing the Amazon rainforest. Millions of tons of African dust travel thousands of miles annually, carrying essential minerals. This dust comes from ancient dried lake beds, ground fine by wind. Phosphorus from Saharan dust feeds South American plants. Earth's systems connect across continents, desert and rainforest. Separated by ocean, remain linked through wind and dust. Stone endures far longer than life. Trilobites that swam 500 million years ago are now fossils in rock. That rock may last another billion years. Dinosaur footprints preserved in stone outlasted the dinosaurs by 100 million years. Human structures, buildings, monuments, cities will crumble to dust while the stone they're built upon remains. Rock is patient. Rock remembers. Volcanic islands are newborn land. Hawaii, Iceland, the Galapagos, all rose from the ocean through volcanic activity. They're mountains built from the seafloor by countless eruptions. New land is still forming. In Iceland, the 2024 eruptions near Grindavik added acres of new Earth. These islands are Earth's creative expression, building land from molten rock, expanding the domain where life can flourish. Minerals grow like crystals from quiet solutions, in caves, in cracks, in cooling magma. Wherever chemical conditions allow, slow precipitation, molecule by molecule, builds geometric forms. Crystals are Earth's architecture, patterns emerging from chaos. Each crystal face follows mathematical rules, beauty arising from chemistry, geometry emerging from solution. Nature builds structure from disorder, patiently. The Pacific Ring of Fire contains most of Earth's active volcanoes and earthquake zones. It encircles the Pacific Ocean where several tectonic plates meet. Subduction creates volcanoes. Plate boundaries generate earthquakes. This ring of geological activity has shaped human civilizations for millennia. People live with this restless geology, adapting to a dynamic Earth. The Ring of Fire reminds us, Earth is alive, active, never static. Gold forms deep underground from hot fluids. Dissolved gold precipitates in quartz veins when conditions change. Most gold is extremely dispersed, a few parts per billion in rock. Economically valuable gold concentrations are rare and precious. Ancient rivers eroded gold from veins, concentrating it in stream gravels. People have sought gold for thousands of years, treasuring this soft, yellow metal that nature creates rarely, slowly, deep within Earth's crust. Beaches are temporary. Sand moves constantly, shifted by waves and currents. Storms remove sand. Gentle weather returns it. Some beaches are advancing, building new land. Others retreat, disappearing over decades. Coastal erosion is natural, not new. What changes is how much we've built on shifting sand. Beaches flow like slow rivers of sediment, constantly rearranging themselves. Mud cracks form when wet mud dries and shrinks. Ancient mud cracks preserved in rock tell us about past environments, places where mud once dried in sun and air. Some mud cracks are billions of years old, showing that Earth has had wet-dry cycles for most of its history. These simple patterns, cracks in dried mud, become windows into ancient climates, preserved forever in stone. Some researchers estimate that in roughly 1.5 billion years, Earth's mantle may cool enough that plate tectonics gradually slows and eventually stops. This is a first attempt at such a distant prediction, and much remains uncertain. But eventually, the geological engines that have shaped our world for billions of years will quiet. Mountains will stop forming. Volcanic activity will fade. Erosion will continue, gradually flattening Earth's surface. Fossils are time's artwork. Delicate fern leaves pressed in shale, shell spirals in limestone, dinosaur bones mineralized to stone. Each fossil is a collaboration between life and geology, biology providing form, minerals providing permanence. Most organisms leave no fossils. Those that do become messages from deep time, whispers from vanished worlds, preserved by fortunate burial and patient mineralization. Basalt forms most of Earth's ocean floor. This dark, dense rock emerges from mid-ocean ridges as lava, cools quickly, and spreads sideways. Nearly all ocean crust is basalt. It's also common in volcanic islands and continental flood basalt provinces. Moon rocks brought back by Apollo astronauts are largely basalt. Mars's surface is mostly basaltic. Basalt is Earth's most common volcanic rock, yet largely hidden beneath seas. Sandstone was once sand. Beaches became rock. Dunes became stone cliffs. Individual grains of sand, each worn from older rock, were cemented together by minerals precipitated from groundwater. Some sandstone still looks like frozen sand. You can see individual grains, layers from ancient dunes, ripples from vanished waves. Sand remembers its origin even after becoming stone. Earth's crust is thinnest beneath oceans, thickest beneath mountains. Oceanic crust averages 4 to 7 miles thick. Continental crust under mountains can be 45 miles thick, like icebergs. Mountains have deep roots extending downward. This is isostasy, Earth's crust floating on the denser mantle below. Mountains stand tall because they extend deep, finding balance between height above and depth below. Feldspar is Earth's most abundant mineral. It makes up about 60% of continental crust, yet few people recognize it. Feldspar weathers into clay, the basis of ceramics and pottery. Ancient cultures unknowingly shaped feldspar's weathering products into vessels, building materials, art. The most common mineral, overlooked yet essential, quietly dominating Earth's crust, slowly transforming into the clay that humans have molded for millennia. Rivers eventually reach the sea. They carry dissolved minerals, fine sediment, and organic matter from continents to oceans. This transfer has continued for billions of years. Rivers build deltas at their mouths, new land constructed from eroded mountains. The Mississippi Delta, Nile Delta, Ganges, Brahmaputra Delta, all represent mountains delivered grain by grain to the sea. Land redistributed through water's patient work. Lava flows can travel miles before cooling. Some flows are thick and slow, others thin and fast. Basaltic lava is hotter and more fluid. Andesitic and rhyolitic lava is cooler and more viscous. Each flow is a frozen river of molten rock, a moment of Earth's interior exposed briefly to surface conditions. Hardened lava preserves flow patterns, bubble textures, the memory of molten movement. Calcite is limestone's main mineral. It forms from calcium carbonate, shells, coral, chemical precipitation. Calcite dissolves in weak acid, which is why limestone caves form. Calcite crystals are common and varied. Iceland spar, clear calcite, has unique optical properties, bending light in interesting ways. This simple mineral builds vast limestone formations, spectacular cave decorations, and humble chalk, abundant, varied, essential. Earth's geological future extends billions of years. Continents will merge again. The Atlantic will eventually close or the Pacific disappear. A new supercontinent will form around 250 million years from now. As the sun slowly brightens over hundreds of millions of years, Earth will eventually warm enough that our oceans begin to evaporate. Perhaps in about 1 billion years, though models vary. But tonight, water still flows, clouds still form, and life continues its ancient relationship with this blue planet. Stone walls built by humans will outlast their builders by thousands of years. The pyramids are 4,600 years old, and could last millions more. Stone artifacts from early humans survive hundreds of thousands of years. Geological materials outlast biological ones. What we build in stone becomes part of the geological record. Future fossils of human civilization, preserved in Earth's patient archive. Water carved the Grand Canyon, exposing 2 billion years of Earth's history in colorful layers. Each band of rock represents a chapter: ancient seas, rivers, deserts, volcanic activity. The canyon continues deepening as the Colorado River cuts downward. It's Earth's most spectacular geology textbook. Pages written in stone, read from rim to river. Time visible in cliffs and slopes. Geology operates on its own timescale, measured in millions and billions of years. Human lifetimes are brief moments. Civilizations are flickers. Yet even in this vastness, each moment matters. Each grain of sand, each raindrop, each breath contributes to Earth's ongoing transformation. We are part of geological time, participants in processes older and longer than comprehension. Earth is a living planet, geologically active, constantly changing. Plates move, mountains rise and fall, oceans appear and disappear. Life and geology shape each other. This dance has continued for over 4 billion years and will continue long after us. We witness one brief moment in Earth's vast story, and it is enough. This moment, this night, this shared stillness, enough. And so, our quiet journey through Earth's geological story comes to a gentle close. We've traveled from Earth's ancient beginnings, when magma oceans cooled beneath alien skies, to today's familiar landscapes still slowly shifting beneath our feet, discovering along the way that time itself flows differently through stone. From the grinding patience of plate tectonics to the sudden violence of earthquakes, from minerals forming grain by grain to mountains rising and falling like slow breath. We've glimpsed how geology is both immeasurably gradual and unexpectedly dynamic. Geology reminds us that permanence is an illusion, that everything solid eventually transforms. Much of Earth's deepest changes happen in silence, far beneath our awareness, in darkness and pressure where rock slowly flows like viscous honey. Stones teach us patience, remind us that gradual processes can accomplish what force cannot. Without geology's slow recycling, without plate tectonics and volcanism and erosion, Earth would be a dead world. By pausing to notice, we glimpse the extraordinary in the ordinary, every pebble a fragment of deep time. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about unity of every atom, every event, every moment in the universe. You are not separate. You are a link in the endless chain. Think about how water cycles through clouds, rivers, oceans, and rain. Everything is connected. Everything returns. Everything flows. You are part of that flow, that cycle, that eternal return. Let your entire being dissolve into the rhythm of nature, into the breath of the earth, into stillness. Prepare for deep sleep. No boundaries left, only peace. If these calm stories from Earth helped you breathe a little easier, passing them along could help another tired soul drift into rest. one quiet share, one peaceful night at a time. But there's no need to do anything now, nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of geology to fade now, like sediment settling through still water, leaving only the deep mineral calm behind. Let your breathing deepen. Let your body feel heavier, as if slowly becoming stone yourself. If sleep comes, let it carry you like a river flowing to the sea, smoothly, inevitably, into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, the continents will still be drifting. Erosion will still be wearing down mountains. Volcanoes will still be building new land. But tonight belongs to stillness. Rest well, weary traveler through deep time. And remember, every rock beneath you carries 4 billion years of memory, and you rest upon that ancient foundation. Dream deeper with bedtime science. Good night.